So this first part we've already kind of talked about, I think. But indications that a chemical reaction has occurred, there is heat or light produced. When we burned magnesium, we got that really bright light, and that was an indication that a chemical reaction was occurring. The production of a gas. What would happen if you have a gas formed? What would it do? Rise up and it bubbles out of solution, yep. And formation of precipitate, forming a solid. That's what we're going to be looking at mostly, is when a solid is formed within two liquids. And those are called precipitates. So a precipitate is insoluble. A soluble substance means it's going to dissolve in water.
Liquids and it makes a solid.
Those are precipitates.
Or maybe it's I don't know, it's two something. There's only one of them.
There's only one of them?
It's two either gases or liquids.
I'm not sure.
Two salts.
I don't know.
I don't know, there's two chemicals and they're the only two that do this. I think it might be two solids make a liquid. But it's just two solids that make a liquid. Just cornstarch water. But like, solid with
I'm not for sure. So we've seen these symbols before. Remember that the down arrow means a precipitate or solid is formed. Gas product would be an up arrow because it bubbles out. You have an arrow or a triangle also, and the triangle means that heat has been added. Aqueous means it's dissolved in water. So it's going to be, well, I guess dissolved doesn't necessarily mean dissociated. So there's two different ways it can be dissolved in water. If it's like sugar, it doesn't split up at all. But ionic compounds will split and dissociate, and we'll talk about that. Yep. Triangle's heat is added. So solutions, there's some terminology we need to know. A solution is a homogeneous mixture. What does homogeneous mean? Same throughout, yep, uniform. And it's a mixture of two or more substances. And the solute is the substance that's present in smaller amounts. So if you think of salt water, what would be the solute? The salt. If you have the solvent is the substance present in larger amounts. Salt water, solvent would be water. And anything that is dissolved in water is called aqueous. So if you have anything that's dissolved in water, aqueous solution. So the solutes can fall into two categories. It can be an electrolyte or non-electrolyte. If it's an electrolyte, when it's dissolved in water, it conducts electricity because it has split into its ions. And so it can conduct electricity. A non-electrolyte does not conduct electricity. And you can have weak or strong electrolytes, showing how easily it can conduct electricity.
Why does salt dissolve?
Because it's polar, and so water will kind of pull it apart.
So if you add enough salt that the salt stops dissolving into the water, does the water become solid?
Yeah, I don't know that it's possible. I don't know. If you had a cup of salt with a drop of water, then I would say yeah. But once you got to the point where there'd be salt or water on top of the salt, then it's not a homogeneous mixture anymore either, because it has to be a solution.
So to figure that, you just measure the grams?
Yeah, I would say they'd go by, or moles. I wonder if it goes by grams or moles. One sec. So I'd say even if you keep adding salt and you get to a point where it doesn't start dissolving, when you get salt on the bottom, it's no longer a homogeneous mixture either. So it's not a solution anymore. So this picture here is, there's electricity coming through this, goes down this wire. It has to be able to conduct the electricity across the solution in order to get the light bulb to turn on. So non-electrolyte, when you have this here, this would be like sugar water. Then there would be no current going through the water. So it's a non-electrolyte. A weak electrolyte would slowly or not very much current is able to pass through there. So it's a weak electrolyte. Whereas a strong electrolyte conducts that current through the water. So that would be like salt water. No.
So you just like salt water?
Yep. If you had, Gatorade would do that. It's full of electrolytes. If you had distilled water, or not, I should say deionized water, so there's no other ions in it, it's just pure H2O, it would not get electricity. So if you're taking in pure H2O, you wouldn't get electrocuted. Yeah. I wouldn't go try that at home. Okay.
Yeah, but if you dump that in your bathtub, things would probably get into it pretty quick.
Yeah, I would say so. Because the stuff that comes out of the tap, it has like some copper ions and other ions in it already. And those ions are what helps conduct electricity. So. No. No, don't do that. Hydration is when ionic compounds dissociate, meaning they split apart into their ions, and the water molecules then surround those ions, and they kind of just pull them apart because water is polar. It has a positive and negative end. The oxygen is more negative, so it's going to attract to the positive part of the ionic compound and pull it away from the negative, and the hydrogen part of water is more negative or more positive, and it's going to attract to the more negative part of the compound, and they just kind of pull it apart. And then they surround, and they do kind of make these little rings around it, just how water orients itself, and surround it in water then. And the reaction can occur in both directions. And so forward reactions is when they're having the reactant turning into product. Reverse reaction is when the product turns into reactant, and that will actually occur back and forth. And when it gets to equilibrium, you wouldn't see a net change in the amount of product and reactant because they're changing at the same rate. And so there's no net change. You wouldn't actually see a net change in reactant and product. So for dissociation equations, if we write the dissociation equation for these compounds, NaCl, hold on, I'm waiting for the pen to show up. Whose is that? The green one? So NaCl breaks into its ions, and what are the ions that make up NaCl? Na plus what? Cl minus. So that would be your dissociation equation. So NaCl yields Na plus Cl minus. How about this magnesium hydroxide? What would it yield? Mg2 plus OH minus. Is it balanced? I have 2 OH minus, right, 2 hydroxides. How about the bottom one? PO4, 3 minus. Yep. Is it balanced? How many bariums? Phosphates? Yep. There you go. Okay, those are dissociation equations. So sometimes when we have two aqueous solutions and they're mixed together, they will form an insoluble product, which would be a precipitate that comes out of solution, because the ions that are in the two separate solutions, once you pour them together, are able to mix. And maybe the cation from the one solution, when it mixes with the anion of the second solution, that forms an insoluble compound, and right away that would form a precipitate. So we're going to use a solubility table to predict if the precipitate will form. And it's on page 98 in your book, or I have one here for you. So we'll go through how to use this table. Kind of look it over. This is just another table that gives you the same information. So let's figure out if these are soluble or insoluble. Calcium phosphate. So on this chart, you want to look for calcium or phosphate. Okay, I see phosphates here towards the bottom, PO4. And they're under the insoluble ionic compounds. So phosphates are insoluble, except there are some exceptions here. If you have ammonium, and we have calcium, not ammonium, or the alkali metals. Is calcium an alkali metal? Where are the alkali metals located? Far left, they're group 1, right? So calcium is not an alkali metal, so it is not an exception, so that would be calcium, it's an alkali earth metal, yes. So this would be insoluble. Because phosphates are insoluble unless it's one of the exceptions. It's not an exception. How about silver sulfate? Sulfates are the bottom ones under soluble. So sulfate is soluble, except has strontium, barium, mercury, and lead. Let me look. Does someone have their book handy? Turn to page 98. Where are the sulfates at? It has silver on there too. I thought so. Silver and calcium. Add on the exceptions, because your book has silver and calcium as an exception also. So add silver and calcium as an exception. For sulfates. As an exception, silver and calcium. So you can see there's going to be a little bit of differences between some solubility charts, but we're going to try to keep everything uniform. Calcium. So would silver sulfate be soluble or insoluble? Insoluble. How about calcium carbonate? Carbonates are insoluble, except those that are of ammonium and alkali metals. So it's insoluble. And sodium phosphate. Phosphates are insoluble except ammonium and alkali metals. So it's soluble. It is an exception. Sodium is one of those exceptions. So this next question says, will a precipitate form when solutions of ammonium sulfide and cadmium nitrate are combined? So if you have ammonium sulfide in solution, cadmium nitrate in solution, and you mix them, now ammonium is able to maybe form a solid with the nitrate or cadmium with the sulfide. So we got to check those two possibilities. So nitrate and ammonium. So ammonium nitrate. Nitrates are the very top one. They are soluble and there's no important exception. So would ammonium nitrate be a precipitate? It forms a solid? No, because it's soluble. Insoluble compounds form solids. So that's not a precipitate. And then we got to check cadmium sulfide. The sulfides are the top insoluble. And is cadmium one of the exceptions? Nope, so it is insoluble. So what precipitate would form? Cadmium sulfide would form. So yes, a precipitate would form, and that precipitate is calcium sulfide. So we're going to use that information when we look at types of equations. There's molecular equations where all the compounds are written in whole units. That's what we have looked at and dealt with so far this year. Ionic equations are when the soluble compounds, so anything that has an aqueous solution, they are actually written as ions, as they would be because they're split as ions in solution. Any precipitate or solid would not be written as ions because they are not in solution. And then the net ionic equation is where spectator ions are not included. What would be like if at a sporting event, where are the spectators or what are they doing? They're just watching. Are they involved in the game or anything? No. So the spectator ions are the ions that aren't really involved in changing state. They aren't involved in the actual chemical reaction. So they're going to be taken out because they don't really have anything to do with the reaction. So here are some examples. If we have two solutions forming or combined, so here's lead nitrate and sodium iodide. They're combining. If you looked on your solubility chart, you'd see that lead iodide is a precipitate that would form. This equation is called the molecular equation. If we want to split everything that is aqueous into ions, we split all these up into ions. Now the solid precipitate, we do not split into ions because it's not dissolved in water. And this is the ionic equation. So what are the spectator ions in this case? Has lead changed states? Lead has gone from aqueous to solid, so it has changed states. So that's not a spectator ion. Nitrate has started as aqueous, ends as aqueous. Would that be a spectator ion? Yes, so nitrate would be a spectator ion. We'll take the nitrates out. How about sodium? It's a spectator. We'll take sodium out. Iodide? No, it has changed from aqueous to solid. So our net ionic equation has taken out the spectator ions. You're left with those, the lead and iodide. So let's try an example. Oh, this is a picture just showing what's happening at the molecular level. where we have this like potassium, lead, iodide, and nitrate, where they're all kind of separate at first, and then the lead and iodide will form its own crystal down here, a solid out of solution. So predict what happens when potassium phosphate is mixed with a calcium nitrate solution. Write the net ionic equation for the reaction also. It's going to be easiest at first to start with a molecular equation, then write an ionic equation, then a net ionic equation. So our molecular equation is, we need potassium phosphate. What's the equation or the formula for potassium phosphate? PO4. Is that it? Yep, K3PO4. Okay, let's check these. Let's make sure we write out the states. It'll help us later on. So potassium phosphate, is it soluble or insoluble? It's soluble, right? So it would be an aqueous solution. Plus, what's the next one? What is it? Calcium nitrate. So calcium NO3 parentheses 2. Is calcium nitrate soluble or insoluble? Soluble, so it's aqueous. And we're yielding. So our possible reaction, the possible products we could get was with everything just kind of switches spots. So what would we have? Calcium phosphate is Ca3PO42. So calcium phosphate, is that soluble or insoluble? Insoluble, so that's going to form a precipitate. So I'm going to put a little down arrow showing that it's a precipitate. You could put S in parentheses, that's fine too, whichever way you want to write it. Plus calcium or potassium nitrate is just KNO3. And nitrates are all soluble, so I'm going to put AQ behind it. So there's our molecular equation. Is it balanced? No. How would we balance it? To put a 3 here?
Yes.
Okay. And now look at our nitrates.
Yeah, those are
Put a 6 here. What would I put here then? A 3 there and 2 there. 6, 2, 3, and 6. Yep. I'd say that looks good. So now let's write our ionic equation. That way we can tell what's our spectator ions and what isn't. So we would have, how many potassium ions do we have? 6, don't we? 6 potassium plus 2 phosphate. Now since this was aqueous, we want to split it into ions. Same with the calcium nitrate. So we have 3 Ca2 plus 6 NO3. Do we split the calcium phosphate into ions? No, because it's the precipitate. So we leave it as a molecular formula. Now the potassium nitrate is aqueous, so we'll split that up. There we go. What are our spectator ions? Potassium and nitrate. So our net ionic equation would be calcium ion plus the 2 phosphate ions. That's supposed to be 3. Yielding that. If you notice, it kind of looks a lot like, well, it's the opposite of a dissociation equation. You're taking ions and forming then a solid. Yep. Potassium nitrate. So we took out the potassium and the nitrate from both sides. Yep. It's kind of like a math equation where you can cancel out anything that's on both sides. Yep. So what's the next one? I think this is the last one we'll do. Can I look? What's next too? Yep. Last thing. We'll do this last one. So what's our molecular formula? We have aluminum nitrate with sodium hydroxide. So what's aluminum nitrate? Is aluminum nitrate soluble or insoluble? So it'd be aqueous plus sodium hydroxide. Is that soluble or insoluble? We haven't looked up hydroxides yet. It's hydroxide are insoluble except the alkali metal cations. Sodium is an alkali cation, so it's an exception, so it's going to be a soluble. So the possible products is if we flip-flop everything. So aluminum hydroxide. Hydroxides are insoluble except alkali metals, ammonium, calcium, strontium, and barium. So is it an exception? No. So that will be our precipitate. Plus then sodium nitrate. Nitrates are soluble with no exceptions. So this would be aqueous. So our ionic equation, well, is it balanced? Should check that. No. How would we balance it? Three here. And a 3 here. There we go. So if we want our ionic equation, we would have split everything into ions that are aqueous. So we'd have Al3 plus 3NO3 minus ones, plus we have 3 sodiums and 3 hydroxides. Our precipitate we do not split into ions because it's solid. Plus then our 3 sodium ions and 3 nitrates. So what's our spectator ions? Sodium and nitrate. I'd agree. I'll underline them for you. So there's our spectator ions. So our net ionic equation would be because it's not, they haven't dissociated. They aren't dissolved in the water. There you go. Questions on the 3 types of equations? Okay, this will not be due until
Next quarter. Next year.
let's go Wednesday. Do Wednesday.